MGF 1107, Chapter 13, Section 3 deals with what we call Hamilton paths and Hamilton circuits. Now, first of all, everything we've done in this Chapter 13 deals with graph theory. You need to understand that graph theory is not what you're commonly used to, say, in algebra or pre-calculus, things like that. This graph theory is using vertices and lines, which we call edges, to indicate a most economical way to travel, most economical way to deliver things, most economical way to just see how things work. Graph theory can be used to solve routing problems. UPS, FedEx, the Postal Service, the airline companies, and so on and so forth use graph theory to find the least cost route. All right, let's talk about Hamilton paths. Hamilton paths contains each vertex of a graph exactly one time. Hamilton circuits begin and end at the same vertex and passes through all other vertices of a graph exactly one time. Now, you may think that this sounds like the Euler definition that we had in section 1. It's not. Euler's definition dealt with edges, that you could only pass through one edge one time. Hamilton circuit means that you need to pass through each vertex one time. That means you don't have to use all the edges. You don't have to use all the paths. In Euler's circuit, not only did you use all the vertices, but you used all the edges. Hamilton, you do not have to use all the edges. Numerically, mathematically, to figure out the number of unique Hamilton circuits in a complete graph is n minus 1 factorial. To look at definitions of, look at some examples of factorial, we can go right here. This is example 3 on page 827 of your textbook. And it says, how many unique Hamilton circuits are in a complete graph with the following number of vertices? See, n in this particular formula is the number of vertices. Okay? So the first problem is saying, okay, we have 4 vertices. So we go 4 minus 1, we have 3 factorial. The factorial sign means we go 3 times 2 times 1, which is 6. Factorial just means whatever number you're starting with, you just keep going down till you get to 1 and you multiply. Like for instance, letter B is 7. So we have 7 minus 1, which is 6 factorial. So we have 6 times 5 times 4 times 3 times 2 times 1. 9 factorial. We go 9 minus 1, which gives us 8 factorial. 8 times 7 times 6 times so, and so on. Let's talk about the definition of a complete graph. A graph that has exactly one edge between each pair of its vertices. All right? So that means you need to connect every vertices to every other vertices. It says every complete graph has a Hamilton circuit. Okay. So looking at letter A here, this is a complete graph because if you look at all the vertices, A is connected to B, C, E, and D. Okay? And so on with the other ones. So this is what we call a complete graph. Letter B is not a complete graph because A is not connected to D, A is not connected to E, and the other ones are connected to all of them. So that's the definition or examples of a complete graph. Other examples of complete graphs are here. This is on page 826 of your book. Okay. And make sure you understand that in a Hamilton circuit too, it begins and ends at the same vertex. It only passes through each vertex one time. That means you don't have to it's not like a Euler one. And I can't emphasize this enough. Euler says you have to go through each edge one time. not each vertices. You can go through vertices more than once. And here's an example problem I want you to look at. It says Keith Urban, Jennifer Lopez, Harry Connick Jr., and Ryan Seacrest, the cast of the television show American Idol, are in Hollywood, represented by an H. They need to travel to the following cities to judge contestants. Auditions are in San Antonio, East Rutherford, Birmingham, Memphis, and Seattle. Okay. Says in how many different ways can the cast travel together, visit each of these cities, and return to Hollywood? Okay, so first of all, here's our diagram. Notice that right here is Hollywood. We've got San Antonio, East Rutherford, Memphis, Birmingham, and San Antonio. I forgot what the S was. But notice that this is a complete graph because Houston's connected to 1, 2, 3, 4, 5. In other words, each vertices, because we have 6 destinations, okay, each vertices is going to have 5 lines because they're going to be connected to the other 5 places. And so what happens is we can figure out how many circuits we have. Because we have 6 vertices, we use the formula. 6 minus 1 gives us 5 factorial. 5 times 4 times 3 times 2 times 1 is 120. So this particular graph right here has 120 different Hamilton circuits. Now remember, Hamilton circuits don't include all edges. They just include the vertices, each vertices once.